Okay. Yeah, so basically stepwise regression is you keep adding one feature uh, on top of the other, and you add the feature which gives you the best improvement. Um, and in stage wise, what you do is you just regress on the error um, between the target and whatever you have chosen as the features, right? So that's the main difference between the stepwise and stage-wise integration. Um, I mean, you can read more about these things in the link that I've given, and I think you will get the access to the slides. Yeah, so how many of you know perceptrons? Does anyone know perceptron? Okay, so uh, why do we use it? I mean, this is an interaction session, so that's why these live sessions have been created. So you guys can talk. Okay, so basically, um, perceptron is a classifier. I mean, whenever the data is separable, right, that means you can draw a line to differentiate the data between positive and negative examples, right? In that cases, perceptron will algorithm, right? So in that case, perceptron algorithm will give you the line that can separate your positive and negative examples. Right? It is very simple. So this dotted lines represents your W transpose X is zero. That's a hyperplane. In two-dimensional thing, this is represents a line, right? And um, so what is a perceptron? It's whenever you have a negative example, right? A negative in the sense you classify it as negative. How do you detect that? That is given by this condition. right? So basically, yeah, that's it. So whenever you make a mistake, you do an update, right? And when you don't make a mistake, you keep the same weight. So yeah, so that's it. So that's perceptron. So at the end, you will find a hyperplane that can separate the data. And this will work if your data is separable, right? So yeah, coming to SVMs, right? So you can see this. These are cross marks and there are some red circles. Right? Cross and red circles. Yeah. So here you can see the blue cross and red circles. So you're supposed to classify the blues on one side and the reds on other. Given this data, you have many hyperplanes that can solve this. Right? And green is also one. And the dotted line is also one. Right? So which line one should pick? Right? So that question is answered in this supported conditions. Yes, now we this is the concept of margin, right? That is nothing but the distance between your line, that hyperplane, the separating hyperplane, to the closest point of your training data. So in this case, this thing can be margin, right? Right. So that is nothing but this thing. This given by this, right? So your minimum distance, right? If you fix W, yeah, only the minimum over your examples gives you the margin. Right? So if you don't have that, W is not fixed. You want to minimize that worst case distance, maximize the worst case distance, right? Among all your training samples. And the algorithm that is used to compute the hard SPM is this thing. You minimize the norm such that you have this constraint. Right? The W transpose xi plus b should be greater than or equal to 1. This yi is the label, belongs to plus 1 or minus 1. So whenever this is greater than 1, you are classifying it correctly. So this assumes that this setup assumes that the data is separable. In that cases, it gives you a line with maximum margin. Any questions here? This is just warm up. I just want to test these things before we solve some problem. Yeah, please you can ask a question.
So why we are considering yi over there for a
Why
class?
I?
We are considering the inner product of xiwi. That is
Right,
the two different features we are taking.
right.
So two different classes there. So we are taking. But why we are considering yi over there?
Why I? Right. Okay. So
Yes,
basically, if you see, right, right, this thing will go here, right. So this is the direction of W. Okay.
sir. Please in the slide.
Yeah, this is the direction of W, right.
Yes, sir.
And let's say this is the direction of your input Xi. Okay.
Yes, sir.
And This makes an acute angle, right, less than 90 degrees. So your dot product is positive for this example, right? And let's say this is labeled as plus one, right? So now when we multiply this y times w transpose x, it is positive, right? Suppose by chance you have this minus here. Let's say it is here, right? So what happens there? Your w transpose x will be positive, and you have y that is negatively labeled, right? Now when you do y times w transpose x, right, and then that will be negative basically. Right. So your decision rule is something you decide, right? W transpose x is greater than zero. I assign plus one, a label of plus one, right? Positive example. W transpose x is negative. I am assigning it a negative label, right? Now only when yi times your W transpose x is positive, then you are making a correct decision. If your decision rule is this, like W transpose x is positive, I'll assign plus one to that label. Now is that clear?
Yes.
Yeah. So why W transpose X is greater than zero is positive example is you can assume you can consider this as a motivating example, right? W transpose X is positive if your W direction and X makes an acute angle, right? Less than 90 degrees, right?
Yes.
Yeah.
And the B is the bias over here.
These are bias. Just ignore that bias because you can always move things up, right? Yeah. B is the bias. That's right. And you know how this problem is converted to the right side problem.
Yes, sir.
Yeah, that is important. I mean, you guys should read the lectures, right, to understand things better. I mean, if you have any doubt, you can ask me. I can explain why this one has come and why this norm has come here. Right here you don't have that. This is the actual stream problem. This is the actual stream problem. This is difficult to solve, so you convert your problem into this fashion. Right. Okay. So coming to soft SVM. Now, so in the bottom, so these are the resources from here. I have taken this pictures and equations. Okay. You guys can read, uh, refer to these things. Okay. And soft SVM is a relaxed version of the hard SVM, so you can allow some mistakes because when you have the data, it need not be separable. So you compromise with that thing, like I mean, I am okay classifying few mistakes, but still I want you know um, with minimum number of mistakes I would like to classify, right? So that's the thing. So that is soft SVM. Now what is zeta I? So zeta is our sort of slack parameters that you introduce um, to measure your this thing, right? The mistakes, the margin uh, of the mistakes. So just to give you what the zeta I mean, it's difficult to explain. The picture is better, right? So I just taken this picture from the Bishop book. Right? You guys can refer to this later on. So when now this is a say plus one, this green color, and this say yellow or golden color, you can call it as minus one, right? And when you have this plus 1 here, right? I mean, I am classifying this correctly, so I don't need to penalize this point. So that's why I assign a slack of 0. Zeta is 0, right? Because it is already correctly classified. And now this is my margin, right? Now this line, blue line, satisfies that W transpose X plus Y is equal to 1, right? And so does the blue line. And between this red and blue, my zeta is less than 1, right? And if my blue point falls to the left of the red line, right? So I'm classifying it as negative. Now, in that case, your zeta will be more than 1, right? So you are expressing your unhappiness more here because this point is negatively classified, though it is positive. Because here it is positively classified, that's why you have assigned a weight of 0, right? So that's how you introduce these zetas as a slack variables, and that's it. And then you sum up and minimize this along with your the original formulation, right? And these are your constraints. So by the way, these are the support vectors, these blue lines. So where you hold this inequality with equality, right? The data points, those points are the support vectors, and you can have any number of support vectors for that matter. Any questions?
So we will penalize the data points when it is far away from the class.
Yeah. So if it is more than, let's say you have set your margin to 1 in this case here, right? And let's say you have y times w transpose x plus b uh, is more than 1, right? Then you are more than okay. So you don't penalize that point. So zeta is 0 for such points. So that example is this way. Right? Here, for this point, you have w transpose xi plus b times that y, which is the margin for that point, is much more than 1. So this blue line is the one where you have that w transpose x times y. Um, of course, I'm ignoring b. Okay, whenever I say from now on, I ignore b. You assume that is there. So y times w transpose x is 1 on this blue line, right? Now within this line, your w transpose x times yi is between 0 and 1, right? So here also you are okay, right? You are violating your margin constraint uh, between red and blue, but still you are not on the wrong side of the decision boundary. So your red is the decision boundary.
So if we will not penalize the data points and the data point is far away from the real zero, then the margin between y0 and y is equal to 1 will be
No,
far away.
ideally you want as far as possible if it is on the right side or if it is on the correct side of your decision boundary, right? So this point you don't penalize it because you are very confident on this prediction, right?
Okay,
Because
means if it will be in the right direction, it will be in the right
yeah,
direction, then we shall not penalize.
no, you will not penalize it. You start penalizing only if it crosses your this margin 1. So this is a wrong point, right? This is a, I mean, you have classified it incorrectly. Although it belongs to uh, plus 1 label, you are, because your decision boundary is red, right? Anything to the left, you call it as minus 1, right? Now, because of that thing, um, you are penalizing it more. Got it.
Yes, sir.
Yeah, well, it is confusing in the first go. I agree, but yeah, you just um, read it maybe twice or thrice. You will follow. The reason you do this because the data is not separable, need not be separable. That is not in your control. Right? So you allow some mistakes to happen. Out of 100 points, let's say some like you're okay with 5 points classifying incorrectly is also fine. So so when do you think this all zeta is will be zero? It will only happen when all of these points are on the mm, right side of your decision model, right? That is a perfectly separable case. So when all zeta is zero, right, your problem is nothing but your old problem, same as the other. So here you have the separable case, right? You have a line and then you can say that left you have one class of points and to the right you have another class of points. Okay. Yeah. You have any more questions also? You feel free to ask because this is confusing. Yes, 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 Krishna, ask please.
So there is one thing, in the doubt session. In the doubt section, I have seen that question, and I tried to get the answer of that, but unable to understand. The question is
Which
the XOR truth table. XOR
can you
truth
come?
table when we take 1001 and truth
No,
value which comes out. Will it be the linearly separable or not?
no, right? XOR is not linearly separable because
Why is it so? Because it will have the two different class only. Why we
let
cannot
me
separate
let,
it?
let me show you. Let me draw. I think you can see. Uh, right now, what does this point uh, tells? Let's say this is my x1 and this is my x2. At this point, what do you think? When both are high, your XOR operation will give you zero, right? One will become zero and zero will become zero, right? Right.
Yes, sir.
Yeah. So when it will be one when one is high, one is low, it will be one, right? So let's call one as some cross, right? Now you want to separate cross and zeros with one line. Can you draw a line and separate this with cross and zero?
No.
That's it. So that's why it's not linearly separable.
Then how shall we, if we want to classify these points, then how we can?
Yeah, you should go for a non-linear classifiers. So by the way, when I say it's not linearly separable, it is not linearly separable probably in the domain which you are considering now, right? When you go for non-linear features such as kernels, right? There they can be linearly separable. So what I meant by that is simple. Um, So let's say you have two dimensions, x1, x2. I have give you features, and let's say x or example, right? They are not linearly separable. Now if I transform x1, x2 to some high dimension case, right? Some x1 transforms the features to some x1, x2, x1 square, x2, something, and so on, right? In that space, they can be linearly separated, right? So that's what you exploit by using this kernels. Okay,
Means we have to convert the plain part.
you have to convert the
Within the
data,
kernel, we just
transform the data to high dimensions, to nonlinear features, right? They
basically
require
what
the
we
linear,
with the kernel is that means we are creating with a plane. In the plane, we are exploring our data.
right?
Okay.
Right. Now there might exist some dimension where they are linearly separable. That's all. So that's what you are. Got it?
Yes, yes.
Yeah. So this is confusing. I mean, feel free to ask any questions. I'll try to answer. Yeah, because I think next slide we have some 5 questions that we'll answer. But yeah, any questions on the SVM or perceptron, feel free to ask. By the way, I have so this quantity, right? Yi times W transpose Xi plus B. If this is Xi, let's say this point X is Xi, and when my norm of W is 1, right? You know what is this quantity represents? What does this quantity represents actually? It is nothing but your distance between your point and the line, the
Margin.
shortest distance, right? That's the shortest distance. I mean, this point can have any number of points and distances, right? This is the shortest distance. There's nothing but the perpendicular distance, right? So that's what it represents. If you don't have this norm constraint, you have to divide it by norm of W, right? You can try to prove that geometrically. It is very easy to prove. Analytically, also you can try to prove. Okay, so if there are no questions, we can go and ahead and solve the problems. So just give me 2 3 minutes, okay? I'll be back in time. Okay? Just give me some time, 3 minutes. Okay? Yeah. So let's get started with the problem. There are very easy problems from this. So now you have say one-dimensional data set, uh, minus one comma one. Y is the label. Okay, so minus one, zero, two are the points, and you have labels one, minus one, and one. And this is transformed to the two-dimensional points, and we want to see if the data will become linearly separable or not. Right? So minus one, zero, two. And we have minus one, zero, and two, and you have labels one, minus one, so positive, negative, and positive. And this feature, the one-dimensional feature, is being transformed to two-dimensional features, right? Um, right. So that is one comma x cube, x cube, right? So what? How does it look like, right? Basically, this point, or all will be your features will be along this line. Okay, so one comma minus one will become minus one again. So this is the point, first point, positive label, right? And the second point is this thing. Uh, it has a negative label, and this is another point. Two will become eight. That's it, right? It has a positive label, right? And now tell me, I mean, first of all, in the original space, is it linearly separable or not?
Yes, it is.
How? I
In the
need one
original
line.
space,
I need one line that can separate plus and minus.
no, no.
It's not linearly separable in the original space. And the transform space also, you just made horizontal line to a vertical line. That's it. Even here, it is not linearly separable. Right. So now you can play with this example and say, Instead of transforming from x1 to x cube, you can see what happens if you do say x
X
square
square equal.
x cube, right? Now, in this case, what happens, right? Your minus 1 will become 1 comma 1. 0 will become 0. Here you have one data point with a negative example. And there will be another point 1 comma 1, right? Um, this is a positive example. And there is another point that is 2 comma 8. 2 and 8. Right? This is, am I audible? Right? And this is 1
Yes,
comma
sir.
8. Okay. Yeah, that's it. So here you can draw some line which is linearly separable. So that's what I was saying. So there can be data in some dimension. They need not be separable. But yeah, in some other dimensions they are separable. Right? So that's it. Uh, so what I try to draw it properly going forward. What I have done is I have just transformed the data to whatever it's been asked. So x is being transformed to 1 comma x cube. Right. So it was not separable on the initial space. In the transform space, also your horizontal line has become a vertical line, of course, with some data points spread out more because of the cube operation. That's it. Mm, okay, let's go to second question. Yeah. So you are given an STM and without any penalties. Okay, and assume for simplicity that that is separable out as well. And you have uh, what should I say? When you train initially, you have two support vectors, right? And now you remove the one training point, and then you have trained that point, train the stream classifier again, right? What is the maximum number of support vectors that can that is possible? So basically, you have n examples. You had n examples where you have only two support vectors.
Sir,
Now
R
you need
square
one,
here means in the two, sorry, sir.
two displays.
Yeah, 2D space only. No? Yeah,
Yeah.
it will remain n it is.
Now you have only n minus one examples, right? So
Pardon, sir?
So I think it is n minus one. So let's try to uh,
Sir, one
visualize.
can be one data point cannot impact the whole data set.
Yeah. So let's see.
Can be
I'll
over.
I will present some examples. Then you can see what is happening there, right? I'll prefer dots and dashes for simple reasoning. Okay. So you have only one example here, okay, which is positive, and I have say a negative example here, right? Sorry, a negative example. So one negative example here, right? Dash is my negative example. Dot is my positive. Okay, and I have so many like this. These are all data points. Okay. Now, which points decide my margin? Right? There's one positive and there's one negative. Right? So these are my support vectors. Right? Probably I should my actual classifier will be somewhere here. Right? And my support vectors are here and here. Right? So this is my uh, example, right? And now I remove this example. Let's say if I remove this
Sir,
example,
your screen is sometimes not visible. There might be an internet problem.
oh, is it okay? It is visible now.
Yes, sir, now it is. While explaining, it is not. So, do you please
Okay,
repeat it?
okay, okay. So basically, what I have drawn is I have drawn some positive example here, okay, and a negative example here, right? And there are so many negative examples that are along this line, right? Now, what is my support vectors? I have two support vectors, right? There is one positive example and one negative example. That's the closest one that can make error. Right? Intuitively, they are support vectors. So what I'm saying is, as whatever asked in the question, I remove this point, this negative example, right? And now what happens? Now all these data points will become my support vectors because they are equidistant from they all satisfy that constraint, y times w transpose x plus p is equal to one or whatever threshold. That is because they are having uniform distance from this line, right? All these points. Right now you can see, right, your
Sir,
support vectors are n minus one. Yeah,
sir, the support vector will get impacted only when the minimum closed data set will be impacted. Then only. Else the data set will be on wherever it is in the right class. Then the support vectors will not be impacted for that.
right. That's right. So what I'm saying, that's why I removed the one that is closest to the point, the hyperplane. Now you
But
have
on the question which you have, and there is nothing written over there that we are impacting
yeah.
any data set which is closer.
No. That's nothing has been done by removing one label training point.
Yeah, from one label means we shall not impact, we shall not considering that the closest of that. Na.
But it can be that closest point itself, right?
Okay, means we can consider it as a closest number.
Yeah, go for the worst case. Don't assume the best case scenario.
Okay, okay, sir, okay.
Maximum. See what they have asked. Question is what is the maximum possible support vectors that can result?
Yeah, then it will be sir n minus one.
Yeah. So I have created a case for you in this example, in this screen. where the 10 minus 1 is feasible. Got it?
Yes, sir.
Yeah. So which of these are valid kernel functions? How many of you know what is a kernel? I mean, what are the conditions for uh, you know say something to this to verify if it is a valid kernel or not?
Sir, please, sir.
Hello, can you come again? Yeah. So things to verify is it should be symmetric. I mean, if you permute x and x prime, you should be get you should be getting
It
the
should be
same value.
positive, semi-definite, and symmetric.
Right. That's difficult to verify. So typically, what people do is uh, this thing, kernel function, you should be able to express it as a dot product of two transformed feature vectors. Right. So I mean, in this example, these are they are all are valid kernels. So yeah. So typical things to look for is they should be symmetric. And if it is easy, you should verify if it is if it is a positive definite or not. Or otherwise, you have to see if it can be expressed as the dot product of two transform features. Vectors, right? These three things you should verify. Yeah. So these are just one-dimensional points. Okay. So they are labeled one followed by four zeros and three ones. And the question is, you just have to check which and this is not linearly separable case, okay, because there are zeros that are in between ones and you have only one dimensional space. So you're just asked to verify which of the following is not a support vector, right? Actually, it should be which of these is a support vector, right? So answer will come out to be one, and it's very simple. You just go to scikit-learn and just execute the set of commands, and you should be able to find that. Another question. Yeah, this is again a question on kernel. Suppose you map um, an input point to a kernel of this form x and x square, and another kernel maps an input to in this form, let's say. Other. So, so margin obtained by using kernel one will be more, or kernel two will be. Now, it depends like uh, what margin exactly. mean here, because if you use a normalized version, right, things should not change. Otherwise, this which wherever you're scaling more, there your margin. So if your margin is something, if you mean margin by say y times w transpose x plus b, right? Then it then this a will be correct. But if you have normalized, you normalize the margins, let's say, right? Right? So then it should not change. Yeah, I think that's it. That's all I had for today. Um, yeah, any questions on SVM? I mean, problems were pretty easy, but yeah, the concept itself is a bit difficult. If you have any questions, I can try to answer. No more questions? Yeah, if you don't have any questions, I think then we can stop. The one thing I would like to mention is you have to interact, because otherwise I will bring some set of slides. I'll sort of read through and finish it. Right. So if you ask, then only I know like what what you exactly want, and that I can answer. Because I don't know what's there in your mind and put it in slides, right? So that's why you have these interactive sessions. So feel free to ask. So there's nothing like we don't judge anything here, right? So it's for learning only. Okay, so yeah, try to be interactive from next
Sir,
week onwards.
sir, is
Yes,
the 10x function the symmetric function? Is the
yes. Can you come
10h
again?
is the symmetric?
Can you? I'm not. Your voice is not clear. Can you come again?
Sir, is the 10h is a symmetric function?
Which one? Tan
10h.
HX. Tan HX is it's not symmetric, right? Because you have this cos HX is symmetric. Sin HX is you have this thing, right? E power minus x minus e power x by 2, I guess, right? Tan HX is not symmetric. It is anti-symmetric, I would say rather.
So then how we can consider in a kernel that in a kernel we must have the symmetric and the semi-definite part now.
See, symmetric you have to swap x and x prime, not x with minus x. Wherever you have x, you replace it with x prime. Wherever there is x prime, you replace it with x. Okay, so it's a dot product that is happening, right?
Sir, we are considering as a function which you have shown in the slide. It is in the inner product now.
Right, right. So, uh,
So sir, inner product is not a dot now. It shall be a cross only.
it's a dot product. Inner product is dot product. A transpose B is inner product. Okay. So let's say tan h of uh, tan h of this x1 transpose x2, right? Now you replace x1 with x2, x2 with x1. It is the same thing. Got it?
A little bit used.
Yeah. So you expand that expression, okay? Then replace x prime with x.
Okay.
Yeah, then you will see. Okay then. So let's meet next week. So what are this week's topics?
It is about neural network, artificial neural network.
Okay.